I have been awarded that Oregon Space Grant Scholarship the last 3 years in a row, and that has propelled me to get involved with the program, to get this internship, to do all of this amazing research. And really, I'm standing on the shoulders of giants here. And I owe a lot of my success, not just to my mentors, but to your entire program. For that, I'm eternally grateful. So, I went to Marshall Space Flight Center this summer. I'm Tara Prevost. I'm studying mechanical engineering and aerospace engineering. Ideally, I would like to do both. And I would like to come to OSU. However, right now I am at Portland Community College. So I went to Marshall. I got to work with some of the greatest minds around. My mentor was Jim Richard and David Edelman. They were in the ER-33, which is the Jet Propulsion's department, primarily handling ducts and valves. So I wanted to kind of touch base. I did do one main project that was huge, but David Edelman and Jim Richard provided us with 4 different tasks. And when I say us, I had one other intern that was working with me on 3 of these. So the magnetically damped passive valve is what I'll tell you more about today. But we did do some detailed design analysis on a pneumatic manifold, which is what my friend Shane took charge on. We also helped with a pneumatic actuator for another valve that they were working on. And we did hardware testing for a multi-port valve, which I'll show you some pictures of. So the multi-port valve testing was incredible. It's essentially a valve with 48 different ports that has one actuator that will open and close all of them at the same time. There's a lot of applications to this. The spark came to my mentor Jim because there were applications in oil production. So essentially, if there is an oil spill, you can turn on and off all of the valves at once without having to hunt down which one's leaking. So we got to take it all apart, clean it, put it all back together, be there when they did cryogenic testing on it. So we pumped liquid nitrogen through it, and it just clouded up the whole field. It was amazing. So if you search MPV test at MSFC, you will be able to see a YouTube video of the entire test as produced by Jim Richard, and he demanded it be on YouTube. So I highly recommend checking it out. This is my friend Shane, who I really owe a lot of gratitude for helping me through this internship. The pneumatic actuator here is, we learned the importance of assembly diagrams because they didn't have an assembly diagram, and we essentially had to produce one. But we ended up cleaning it all, replacing the seals. I became a very good seal pro. Omni seals are very special seals that have springs inside of them to expand and contract to maintain the seal's integrity as it undergoes high pressures. But the seals are very expensive. So putting these little teeny seals in, if you just as much as bend one, you're chucking out $70 and putting in a new $70. So I got very good at that, and I was proud of that. We replaced all of the seals, did ultrasonic cleaning of the small parts, and we did preliminary testing like the last week of the internship and showed that it could withstand the proof pressures that it needed to. But this was my baby for the summer. It's a magnetically damped passive valve. So a passive valve, if you can imagine this screwed together, you have flow that comes in, and as the pressure builds, it compresses the spring of the poppet, allows the pressure to go through the valve, and then it slams shut if the pressure isn't maintained. So there's an issue called valve chatter, where essentially the differential pressure drops are causing the valve to slam shut, and it degrades the seals. You can have a lot of resonance issues with other components. So there's a lot of issues with it, and primarily because with rocketry applications, you need really high flow for takeoff, and then really low flow for the duration of its life in space. The low flow conditions causing that chatter would make it impossible for us to, say, replace a valve on its way to Mars. So my mentor said that check valves were the bane of his existence, and I understand now why. They're very simple, but they're pneumatically driven. So there's a wide range of applications for check valves, primarily in rocketry applications for this, but they can also be used in cars and home plumbing and anywhere you need things to flow one way and not the other. So our design, and by our design, I mean my mentor's idea, was to utilize Faraday's and Lenz's laws to eliminate the passive valve chatter. So a little context, has anybody seen a magnet fall through a copper tube? Yeah, okay, so when you drop a magnet through a copper tube, it slows down and almost seems to hover. And it's because the magnetic field lines coming out of the magnet go through the tube, and as it hits the copper, it induces eddy currents, which right-hand rule produce a force in the opposite direction. So it opposes the direction of motion. That was the spark that kind of led to this whole idea. First, my mentor said, we need to model this existing check valve, and I learned to do 3D modeling this summer from scratch. Pro engineer is very difficult, but once I got the hang of it, I was able to model it, as well as the threading, which the threading, I did not know, has an entire science behind it. A lot of mathematics, and it has to do with the stress and strain of how these components fit together. So that alone was a project in itself. But I ended up with my most wonderful 3D drawing here. I'm very, very proud of it, modeling the existing check valve. And then my other portion of this was to model this mathematical phenomenon of the opposing force in an oscillating environment. So essentially trying to write an equation that described how the force reacts as this poppet is opening and closing and shattering. So this was the experiment done before me. So a little context. If you see here, there's a copper tube. The copper tube is on a piston, and it's linearly driven so that there's a magnet on a fixed load cell. And as the magnet, or as the copper tube oscillates up and down, you can measure the force that's produced on the load cell. So they ran this, and they were actually measuring the angular velocity of the machine and not the linear velocity of the tube, which is why a lot of their math behind trying to build it before was inconclusive. But going over all of the data and all of this experiment, I ended up taking this machine apart and measuring out so that I could do the kinematics and figure out what's the linear velocity here. What are we working with in terms of that motion? So the pogo pulsar, as they called it, it was essentially a recycled piece of equipment, but they have found a lot of different uses for it. I mean, having an oscillating piece is pretty handy. So I went through and did all of the kinematics. Essentially, you'll see this is the kinematics portion of the equation that translated what they were measuring in the angular velocity into the linear velocity that was actually happening. So to make it simple, I was handed 112 different graphs. Each graph only had load versus the angular velocity. And those graphs had no timestamps. So using WinPlot, which is actually an in-house program that was developed at NASA by a man named J.R. Moody. He's a genius. He's amazing, and I thank him so much for that program. It made my life very easy. What he did is we would put these graphs in, export them to a CBS file, and then go through, and I added just arbitrary timestamps so that you could actually see the different velocities as it steps up, and as they ramped it up, you can see the force increasing as the angular velocity increased. And then, again, I'm standing on the shoulders of giants. I owe the European Journal of Physics for almost all of this success. They did a lot of work on magnet falling through magnet fall through a copper pipe, which essentially describes the magnetic braking force as a function of the velocity. So this equation I derived from their work, this portion of it anyways, where it's a function of the conductivity of the copper, the strength of the magnet, and the inner and outer diameters of the tube. So after putting all of this together, what they said couldn't be done, I did mathematically simulate within a factor of 2. So I was really proud to see that this is my theoretical model, and it did match the different graphs that we had produced. So we could say, with very good cause, that it was a useful tool and that the science behind it was sound so that we can move on with the prototype development. So that's the math behind it. As you can see, up here I put kind of a diagram of these flux lines. The flux, or the opposing force, is produced by the radial component of the flux lines. So that was really difficult in finding out with these magnets we were just handed magnets and the spec sheet. We didn't have a lot of things to measure the strengths and all of that, so we were relying a lot on K&J Magnetics website to get all of these different variables and translate the variables that we didn't have into yet. So it was a lot of unit conversion. Dimensional analysis I found is very important. So the parameters for the prototype: maximize the radial component of the flux lines in the copper tube, maximize the conductivity of copper, so we chose copper 101. It's very pure, so it actually does get very good conductivity. And we decided to build this because the patent paperwork is already in. I was told I can show you a little bit about the prototype. Essentially, you have the check valve with the poppet, the copper tube, and then the magnet, so that if the poppet begins to chatter at a high frequency, the higher velocity will cause a higher opposing force. So that paperwork is in. Hopefully, my name will be on a patent in the next 6 years. I'm very, very excited about it, and I owe my mentor everything for that. So I have a kind of a diagram of where I think that factor of 2 was missing. Because if you see the purple on the edge of the magnets, it immediately goes to yellow. So if you're thinking a function of distance, a tolerance of a 0.5 millimeter makes a huge jump